The sampling distribution of any statistic is going to depend on both the population distribution as well as on the statistic that's actually being computed. And so in general, it's kind of difficult for us to make very firm statements about sampling distributions without making assumptions about the population or about thinking about specific statistics. Fortunately for us, it's often going to be the case that we're most interested in only a handful of different statistics. And far and away, the most common statistic for us to be dealing with is going to be the sample mean. And so it's worth spending some time to think about what can we say about the sampling distribution of the sample mean, because the sample mean is just so commonly used. And so if there are some statements that we can make about the sampling distribution of the sample mean, then that will better inform any of the statistical inference that we want to do surrounding the sampling mean. So the sampling distribution of the sample mean is going to have characteristics that are defined for all populations, no matter what that population distribution happens to be. And specifically, what I mean by that is that the sample mean is going to have a mean and a variance that are the same no matter what the population is, right? So we will always be able to say that if you're looking at the sampling distribution of the sample mean, the expected value of that distribution and the variance of that distribution are known without knowing anything else about the population. So no matter what the population looks like, we can always make these 2 points. So if we want to start thinking about the parameters of the sample mean's sampling distribution, we can start by thinking about the mean of the distribution. Okay. And so what are we actually sort of referring to here, right? We have to sort of deal with a little bit of notation to begin, right? And so we're going to be thinking about the sample mean of some set of observations that we'll call x1, x2, x3, and so forth, right? And so really, when we're thinking about the sample that we're going to be taking, right, we're going to be drawing values here, and these values are going to be x1, x2, and so forth, right, up to xn. Okay, and then our sample mean that we can think about taking here, right, our sample mean is going to be given then by taking the sum of x1 up to xn and dividing that by n, right? And so we write x bar is going to be our sample mean, which is going to be 1 over n, the sum from I equals 1 to n of xi. And just to make sure that we're understanding our notation here, right, this is 1 divided by n times by x1 plus x2 and so forth, all the way up to xn. Right, so we add up all of the points together, divide by n, that gives us our sample mean. x1 through xn here are just going to be those specific realizations that we get in our sample. So remember, the sample is going to be random, and the specific realizations that we happen to see, that is going to constitute x1 up to xn. We're not going to be assuming anything else about the points here, except we're going to assume that the mean, so the expected value of any of these x's, is equal to mu. Right, so we're going to assume that the mean of x is given by mu. And otherwise, we're not going to make other assumptions here. Okay, so that's the context, the notational context that we're working in here. And there's 2 facts that we want to point out here. So the first fact is that if you have any sequence of independent random variables, then the expected value of their summations is the sum of their expected values. And so when we're writing this down here, right, we're thinking about W1, W2, and so forth. And this is going to be a sequence of random variables. And if you want to know what's the expected value of W1 plus W2 all the way up to Wn, this is the same thing as writing the expected value of W1 plus the expected value of W2 and so forth. And so the expected value is going to be additive in the sense that if you're taking a sum, then you can add up all of the individual expected values. So that's the first fact that's important for us to see. The second fact is that if you have any constant value, then the expected value of the constant times by a random variable is the constant times the expected value, right? So the expected value of some constant c times by x is c times the expected value of x, right? And so if you want to know, well, what's the expected value of, say, 5x, right? This is 5 times the expected value of x. Okay, and so these 2 facts alone are going to be enough for us to make some sweeping statements about the distribution, the sampling distribution of the sample mean. And specifically, what we're going to be able to do is use those two facts to say that the expected value of the sample mean, so the expected value of x bar, is going to equal the true mean, right? So how do we get this? Well, we can look at what's actually written sort of on the slide here, and we can work through each of those steps. So we're thinking about the expected value here of x bar, right? Well, remember, x bar is 1 over n times by the summation of all of our points here. So that's the expected value of 1 over n times by x1 plus x2 and so forth up to xn. Okay, and so now we want to use these two facts. And so the first thing that we're going to do is we're going to use that second fact. And what we see here is that we have this 1 over n is acting as a constant, right? It's a constant times by something else. And so we can pull that constant out front. And this is now 1 over n times by the expected value of that stuff that we have left over. So that's x1 plus x2 and so forth. Right. And now the last piece that we need to do here is we're going to go, okay, well, we can use that first fact to simplify down this expected value of the sum, and that's going to be 1 over n times by the expected value of x1 plus the expected value of x2 and so forth up to xn, right? So that's using those two facts that we have there. Now, the important thing for us to note here, right, is that each of these x's is going to have the same expected value, okay? And so this is going to equal mu, this one's going to equal mu, this one's going to equal mu, right? They're all going to equal mu. And so if you add up n times mu and then divide by n, that total sum is going to give us mu overall, okay? And so overall, that's going to simplify down to this result, which is the expected value of x bar is equal to mu. So the expected value of the sample mean is equal to the population mean. No matter what population we're dealing with, it's always going to be true that the expected value of the sample mean is equal to the expected value of the population. Okay. Now, that's for the mean. We can also think about characterizing the variance in a similar kind of way. And so here, what we're going to be doing is we're going to be taking the same notation that we were dealing with before, right? So we have our x1, x2, and so forth. But now what we're going to also assume is that the variance of each of these points is given by sigma squared. Okay, and it's the same variance for each of the different points here. So now we need two additional facts. So fact number 3 is going to be if we have a series of independent random variables, then adding up all of them and taking the variance is the same as taking the variance of each of those and adding up. So this is exactly like fact 1, except instead of the expected value, we're thinking about the variance here, right? And again, this is a fact that can be proved, but we can take as granted in this case. So if you want to take the variance of a sum, that's the same thing as taking the sum of the variances. Before we saw that if you wanted to take the expected value of a sum, that's the same thing as the expected, or the sum of the expected values. Here, the variance of a sum is the sum of the variances. In terms of fact number 4, again, it looks a lot like fact number 2 that we were looking at, but if we have any constant c, then the variance of c times by the random variable is going to be c squared times by the variance of that random variable, right? So instead of, in the previous case, it was c times the expected value of x, here it's going to be c squared times the variance of x. Okay? And so using those two facts, we can follow a similar process to ask ourselves, well, what's the variance of x bar going to be? Okay, and so if we actually sort of pull out this result here, right, we're going to see that the variance of x bar is going to ultimately equal sigma squared divided by n. But let's walk through that again, point by point here. Okay, so we're going to start by saying, well, the variance of x bar, okay, is going to be equal to the variance, and then we can write in what is x bar here, right? So that's 1 over n, the sum from I equals 1 to n of xi. Okay, and so the first piece that we'll do is we can say, well, this 1 over n term can come out front using fact number 4, and when we pull it out front, it has to get squared. So that's going to be 1 over n squared times by the variance of the piece that we have left over, right? And I'll write out that summation as x1 plus x2 plus all the way up to xn. Now we're assuming that all of these random variables are independent of one another, and so now we can use fact number 3 to actually write down that this is going to be 1 over n squared times by, and then we have the variance of x1 plus the variance of x2, and so forth, right? Plus all the way up to the variance of xn. Okay? And so then, if we write all of this down, right, each one of those variances is going to be sigma squared, and so we're going to get 1 over n squared times by sigma squared plus sigma squared plus, and so forth, all the way up to sigma squared, right? And importantly, there are going to be n copies of this, so that's going to be n, or 1 over n squared, times by n sigma squared, right? We can cancel this n with that n, and we go, this is all equal to sigma squared divided by n as our final answer here, right? And so what we're saying here is that the variance of the sample mean is going to be the population variance divided by the size of the sample that you take. As you take larger and larger samples, your variance is going to get smaller and smaller, which should also make a little bit of sense. So the variance of the sample mean is given by the population variance divided by n. And this is true, again, for any population. Does not matter the distribution of the population. This will always be true. The standard deviation is always the square root of variance, and so if we take the square root of sigma squared over n, that is sigma divided by the square root of n, so the standard deviation is always sigma over the square root of n. And we call the standard deviation the standard error. So when we're dealing with a statistic, specifically with the sample mean, but with any statistic, the standard deviation of a statistic is called the standard error of that statistic. And so we can say the standard error is sigma divided by the square root again of n. Again, this holds for any population. It does not need to follow some specific distribution. So let's walk through just a few examples here. And all these examples are going to do is they're going to present us with a population, and then we're going to try to characterize what is the mean and the variance of that population. Okay. So first, we'll look at a pharmacological trial. And so researchers are studying adults with type 2 diabetes. We're going to say that the population has a mean blood glucose level of 120 milligrams per deciliter with a variance of 25. Sample of size 49 is taken. And what we want to do is we want to say, okay, well, if you're going to calculate the sample mean here, what is the expected value of x bar and what is the variance of x bar? And so remember, the expected value, oops, put that lower down here. The expected value of x bar is always going to equal our population mean, right? So that's going to equal mu. And in this case, mu is just 120, right? We're told that the population mean is 120. And so we know that the expected value of the sample mean here is going to be 120. The variance of x bar is going to be sigma squared divided by n. In our case, sigma squared, we're told that that's 25, right? N, we're told, is 49, and so it's going to be 25 over 49. Now this is going to produce a standard error, right? So we can call standard error SE here of x bar is going to be the square root of this, square root of 25 over 49. Remember, this is just the standard deviation, and the square root of 25 over 49 is 5 over 7. Okay, and so using that information, we can write down what is the expected value and the variance here, right? And so we can fill out all of these pieces of information here. The expected value is going to be 120. The variance is going to be 25 over 49, which if you work out in decimal is about 0.51. The standard error is 5 over 7. Okay, so let's take a look at another example here. And this one's a little bit different. So pollsters are going to attempt to gauge the support for a particular candidate in a region. In the population, 45% of individuals support the candidate, and the standard deviation is going to be 0.2475. Okay. And so then a 100 person sample is taken. So in this question, there's actually a slight typo here. And so specifically, this should say that the variance is going to be 0.2475. So sigma squared is equal to 0.2475, not the standard deviation here. Okay, and we'll see how that matters in just a moment here, right? But we could work it out no matter what. I just know that the answers on the slides are going to use sigma squared here. Okay, so if we walk through what's actually going on here, we can think about the sample mean as coming from a set of binary indicators. And so I'll take just a minute to explain what we mean by this, right? So we can open this up here, and we'll just think about what is it that, or how can we express the sample mean as being how can we express the proportion of individuals who support this candidate as being a sample mean, right? And so the idea here is that what if we were to take xi, right? And what we're going to define xi to be, xi is going to be equal to a value of 1 if the candidate, or if the person supports the candidate. So if person I supports the candidate, and it's going to be a 0 otherwise. Okay, and so here we have xi is going to be defined based on, did you support the candidate or do you not support the candidate? Okay, and then we can think about, well, what is x bar in this case? Okay, so we think about x bar, and x bar, remember, is going to equal 1 over n, and then we add up all of the observations here. So sum from I equals 1 to n of xi, right? And this is 1 over n x1 plus x2 plus, and so forth, all the way up to xn. Okay? And so importantly, if we think about adding up all of these different indicators here, right? If the person supports it, then it might be a 1, right? And if the person does not support it, it's going to be a 0. And so if you add up a bunch of 1s where there's only a 1 every time someone supports it, and it's a 0 otherwise, then all we're doing is we're counting up how many people supported the candidate in the sample that we took, right? And so if you think about it, if the first person supports, then we're going to get a 1 here. If the second person supports, we're going to get a 1 here. Maybe the last person doesn't support, so we get a 0 here. And if you go through and you just say, did you support, did you not support, all we're doing is we're counting up 1s and 0s. We're counting up how many people supported. And so if you were to actually write all of this through, then what you're going to find is that this is going to be the number who support divided by n, right? And n here is the total number, right? So it's the number who support divided by the total number. Okay, and so what we're finding is that the sample mean in this case is exactly going to be the proportion of people who support in our sample. So this right here is going to be our sample proportion. And so what this is really showing us is that if you're thinking about sample proportions, then you can think about sample proportions as being fundamentally no different than sample means. And so everything that we talked about with sample means is still going to apply to sample proportions. Okay, and so that's going to be a really important result for us to use, because anytime that we want to be dealing with sample proportions, we can still use these results for sample means. Okay, so we can clear this away. Open up the slides again here. And so we can think about, well, what's going to be the expected value of our sample mean here? What's going to be the variance? The population is 0.5, right? And so then the sample mean is going to have an expected value of 0.45. Okay, so we have the exact same result applying here. Similarly, the variance is going to be the variance in the population, which again, 0.2475, divided by our sample size, which in this case is 100, so 0.002475. Standard error is the square root of the variance. Okay, and so in this case, as soon as you can think about the proportion as being a sample mean, then we can think about the same results that apply to sample means as applying to sample proportions. And go to a third example here. This one's going to be a little bit more traditional. So we're thinking about agricultural researchers. They're studying the yields of a particular crop variety. The crop has an average yield of 22,000 pounds per acre with a standard deviation of 4,000 pounds. Here, this is actually a standard deviation. Okay, so the sample size is going to be taken over 25 acres, right? So what's going to be the mean? What's going to be the variance? Well, remember, the mean is the same. The expected value of the sample mean is always equal to the population mean. So the expected value of x bar is 22,000. The variance is going to be the variance in the population divided by our sample size. Here we are told that the standard deviation is 4,000. So the variance is 4,000 squared. Divide that by 25 and we get 640,000. The standard error is therefore the square root of 640,000, which is 800. Okay, so we can think about the sampling distribution of the sample mean. And specifically, what we're thinking about is the fact that the parameters that characterize this distribution, so the mean and the variance and the standard error, are always going to be the same no matter what the population distribution is. We know what they are no matter what happens with the population. Unfortunately, the true parameter values are not going to typically be known. In these examples, we were told the population had a mean of such and such value and a variance of such and such value. We're not going to actually know those in practice. And so we're going to need sort of other ways of connecting the sampling distribution to those parameter values. But if we did know those values, then we would exactly know the mean and the variance of our sampling distribution. So in practice, we're not going to have those values, but it's useful to start connecting them up, because what that's going to mean is that the sampling distribution is going to be connected to the parameter values in the population. Okay, so the specific distribution for the sampling distribution is going to depend on the population distribution, right? Just because we know the mean and the variance does not mean that we know exactly what the distribution is. We don't know if these are normal distributions. We don't know if they're uniform distributions, right? They could sort of look like anything, but it's important to know we do know what the expected value is going to be, and we do know what the variance is. We don't know the exact shape, but we know these two properties that start to characterize the behavior here. In order for us to know the specific distribution, we're going to need to know the population distribution itself. So the specific distribution is going to depend on what happens in the population, but the mean and the variance, they don't depend on what happens in the population. Okay. And so the sampling distribution for the sample mean can be characterized in terms of its mean and its variance by knowledge or without knowledge of the population distribution. However, we typically need more than just the mean and the variance, right? We're typically going to need the actual distribution that we're working with here. And so while it's useful that we always know what is the expected value, what is the variance, typically we're going to need some extra results before we can actually do statistical inference with this, right? So we've already been able to connect some of the parameters of our sampling distribution back to the population distribution without that knowledge. But in order to take the next step, we're really going to need to know, okay, so what is the distribution specifically?